Okay, so today I'm going to be deriving Bernoulli's equation for incompressible and laminar flow. Basically, what do those two terms mean? Incompressible just means that the fluid can't be compressed or expanded without changing the pressure or anything like that. And laminar means that the layers of the fluid, when they flow, they don't mix, so there's no turbulence. So I'm going to start with this little diagram here of a pipe. One has a lower area that's a bit more compact, and then one has a higher area that's a bit wider. And the direction of the flow is from left to right. I'm going to do some labeling here. I'm going to say that I'll set a ground level right here, and I'm just going to take the center of this and the center of this. I'm going to say that this pipe right here is at a height y1. I'm going to say that this pipe right here is at a height of y2. Now, other things about the fluid that I'm going to put as initial conditions is I'm going to say that this is moving at a speed v1 this way, and the fluid over here is moving at a speed v2 this way. And then I'm going to assume that the pressure is constant throughout the entire pipe. It's the same fluid, same material. So density, not pressure. Density is constant. Pressure is definitely not constant because the mass flow rate is different on both sides of the pipe because the areas are changing. So, what actually drives this force is, or what drives this flow is a force. So there's going to be a force F1 acting on this side of the pipe, and on this side there's going to be a force acting back this way, F2 acting against the flow. And I'm going to give each of these little regions that I've kind of dotted out here a length, delta x. So this is delta x1, and this is dx2. I'll use d instead of delta because it's easier. Now, how does the fluid actually flow here? This force is doing work, and I'm going to try and express the work in terms of pressure and volume rather than force and distance, and it'll make sense why in a second. So I'm going to say that the change in work throughout the pipe is equal to, we have this force over here, F1. So this is F1 delta x1. And then we have F2 over here acting against the flow. And so that's going to be minus F2 dx2. Now I'm going to substitute a few things. Force, we write down P equals F over A. Pressure is force over area. That means force equals pressure times area. And so we can rewrite this as d work equals the pressure at this point over here, the area, times the delta x, and then the same thing for over here at the other end of the pipe. So this is P2 A2 dx2. And if you think of geometry, what is area times a distance? Well, that's just the volume of this section over here. So this is V1 and V2. But since there's a little dx here, I'm just going to call that dV1 and dV2. So I have this, and what I'm going to do is I'm going to get rid of this for more space. And I'm just going to write this at the top here. So we have dW equals P1 dV1 minus P2 dV2. Now, what is work in terms of energy? Well, it's the change in kinetic energy added with the change in potential energy. So I'm going to write right here that this dW, d work, equals dk for kinetic plus du for potential. What is the potential energy here? Gravitational potential energy. And then the kinetic energy is just the movement of the fluid. So I'm going to write d work equals the change of the kinetic energy, which is just the kinetic energy at the final point minus the kinetic energy at the initial point. So I'm going to write 1/2 m2 v2 squared minus 1/2 m1 v1 squared. And then I'm going to add du. Du is just, well, the same thing, taking the final minus initial, except this time of the gravitational potential energy. So that would be m2g y2 minus m1 g y1. Now, I'm going to switch from mass to density times volume. Using density equals mass over volume, I can rearrange to get mass equals density times volume. I'm going to use that and I'm going to rewrite some stuff. I'm going to rewrite m1 and m2, so I'm just going to say m sub I is equal to the density times dv sub I. So now I'm going to use that, I'm going to rewrite this. So dW equals 1/2 times the density times dV2, times dV2 times V2 squared minus, and then these are two different V's, one's for volume and one's for velocity. The volume term is going to vanish eventually, so that shouldn't be a huge problem. And then this is minus 1/2 rho dV1 V1 squared. And that's the kinetic energy, so I can erase this now. And then so we still have the potential energy, which is rho 2 dV2 times G times Y2 minus rho 1. Actually, there's no subscript on the rho because density is constant throughout. And we have dV1 times G times Y1. And so now you have a much better way of expressing this in terms of the density of the fluid and the volume of the fluid. So now I'm going to take this. This dW is equal to this dW. So now, I'm going to write down here, P1 dV1 minus P2 dV2 is equal to this whole expression right here. But instead of writing that, I'm just going to do this. I'm just going to do this. Saying that this is equal to this up here. So then I don't have to write more. And the next thing I'm going to do is I'm going to try and get all the P1s, dV1s, and Y1s on one side, and then the same thing with the 2s. So I'm going to rearrange this. I want the 1s on the left and the 2s on the right. So I have P1, dV1, and then I'm going to move this on the other side by adding it. So plus rho over 2 dV1 V1 squared. And then I'm going to do the same thing with this, plus rho dV1 G Y1. And then I'm going to say that this is equal to the other side. Well, we have this is a positive term, this is a positive term, and if we add this to the other side, that's also a positive term. And so that would be P2 dV2 plus rho over 2 dV2 V2 squared plus rho dV2 G Y2. And if we assume one more thing, it's that this little volume over here is the same as this volume over here, the dV terms will be the same and they will all cancel. And so we are left with P1 plus 1/2 rho V1 squared plus rho G Y1 is equal to the same thing for the other side. P2 plus 1/2 rho V2 squared plus rho G Y2. And these are equal. So if you've ever taken a class like Introductory Physics or AP Physics 1 or something similar, and you will recognize this as Bernoulli's equation, which is basically just conservation of energy, but for fluid mechanics. Another way you could write this is at each point on this pipe, the pressure plus 1/2 times the density times the velocity squared plus the density times G times the height is going to be constant. And for a flow that is incompressible and laminar, this applies throughout this whole pipe. We're also assuming here that there is zero viscosity, so there's no shear between the different layers of the fluid. That's another thing. But yeah, this is Bernoulli's equation. It's just conservation of energy for a really simple type of flow, incompressible, laminar, no viscosity. But yeah, it works really well. And that's about it. Thanks for watching.